Your part cooling probably looks like this. Meanwhile, the 3D printer she told you not to worry about is printing like this. Wait. Part cooling is one of the most overlooked parts of a quality 3D printer, and I also think it's oversimplified. It's not just blowing as much air as you can onto a part. Today we're going to be taking a look at why part cooling is more complicated than you thought, how to get the best part cooling possible right now, and how to tune your part cooling to get the best possible results. Before we can talk about the complexities of part cooling, we need to understand what part cooling is, why part cooling is, and how part cooling is. Part cooling is the cooling of plastic as it comes out of the nozzle of your 3D printer. This is usually done by directing cool air towards the area underneath your nozzle. So yeah, the what is simple enough, but how do we get part cooling? The most common method is to attach a fan to your print head, which blows air through a duct that directs the air just under the nozzle of your printer. There are a lot of different ways to go about implementing this simple solution, and we'll be taking a look at one great way in this video. However, there are two other part cooling methods which you may or may not be aware of. The first is typically referred to as auxiliary part cooling. This is where fan ducts are mounted to a part of the printer that isn't your print head, say the X-axis gantry on a Bed Slinger, or just to the side of the printer. The advantage of this is that you can fit much larger, more powerful fans to blow air through the ducts that you wouldn't be able to fit on your print head. This is used in cases where extreme cooling is needed, typically in a high-speed printing. The downside of these stationary part cooling ducts is that they can only blow on one specific area of the printer. The ones mounted to the gantry that can move up and down with the print head are better, but the ones that are mounted to the frame of the printer are kind of one-trick ponies. The last method is kind of a hybrid of the first two that I described. It's where you have a very powerful fan or blower off the printer, and it blows air through some kind of hose that attaches to the print head, and then that air is directed to just under the part. So it's great because you still get part cooling right under the nozzle all the time, but you do have a larger hose directing air in. Again, this is only really used when you need some extreme part cooling like in speed printing. So we've got the what and the how of part cooling, so why part cooling? Let's jump into a slicer to check out what's happening when we actually 3D print things. Our slicers tell our printers to extrude these lines, which are about 0.4 millimeters wide and 0.2 millimeters tall. And as our printer goes around, it just extrudes that line. The thing is, when our plastics are extruded, they're still molten. They're not perfectly solid, they're amorphous solids. So you see this line path is extruded over pretty much just thin air. And if that's not cooled, then it's going to be, again, an amorphous solid, which means it won't be completely rigid and stiff. It will continue to flow sort of like a liquid, but it'll bend, and then when it cools, it will finally solidify. This changing of shape occurs for two main reasons. The first, most obvious one is gravity. If there is nothing below the plastic being extruded, as in the case of bridges and more steep overhangs, then the plastic is just going to droop until it cools and hardens. Another reason is that as our plastics cool, they tend to contract. This isn't really a problem for PLA, but in the case of ABS and things like nylon, those plastics, when they cool and contract, they can often peel off the build plate or just morph the part. I printed this Benchy out with no part cooling active, and you can see the hole actually has this concave bit from where the plastic contracted and pulled in. The final main reason is that all the plastic you extrude is connected. So think, as you lay down a bit of plastic, this nozzle is still pulling on the plastic that's been laid down, and this plastic that's been laid down is still pulling on the plastic from the nozzle. This is particularly important when a printer is making corners. If the plastic doesn't cool fast enough, as that nozzle corners, it will pull the plastic with it. All three of these issues can be mitigated by good part cooling. So the ideal part cooling would be one that cools the plastic as fast as possible? Well, not exactly. If you're only printing out artistic models like this Benchy or this cool dodecahedron model, then you probably do just want to blast your parts with part cooling. But if you're interested in printing functional parts or printing with different plastics other than just PLA, then you need to approach part cooling with more nuance. To explain why, we need to understand a few things first. So there's this property of plastics called the glass transition temperature. The glass transition temperature is the temperature at which the molecules inside of our plastics go from being mobile to being frozen in place. This change in mobility is what causes plastics to melt and harden. For PLA, that temperature is about 60 Celsius. But the story still isn't just as simple as our plastics going from molten to solid right when it passes that temperature. In fact, something I'd love to do a deep dive into in a future video is that actually how long a plastic takes to cool vastly changes its mechanical properties once it is cooled. A simple analogy for this is like a blacksmith that has just smithed a sword and it's still red hot. Usually they dip the sword in water to cool it extremely quick. Well, that sword is going to have different properties than a sword that was set down and just cooled in the air slowly. To understand why the mechanical properties change depending on how our plastics are cooled, we need to take a step back and look at the chemistry of our plastics. The plastics we use are made up of polymers. Polymers are long chains of identical units called monomers. This is a PLA monomer. These monomers are chained together with very strong bonds. Ideally, our plastic could just be one long polymer chain because it has such strong bonds between the monomers, but that would be incredibly thin. So what our plastics actually are just a bunch of these polymer chains just kind of stacked with each other in like this big glob. But there aren't very strong bonds that hold one polymer chain to another. The forces that are holding our polymer chains together aren't really strong chemical bonds like the ones holding the monomers together, but they're weaker bonds. One of them you might know is referred to as hydrogen bonding. The other is a very weak force called the van der Waals force. So when we heat up our plastics beyond their glass transition temperature, these bonds break, and that's why all these polymers become mobile. When we cool our plastics below the glass transition temperature, these bonds reform. But there's a small range of temperature in here where the molecules are still sort of mobile, but what they're doing is they're kind of reorienting themselves and forming these bonds. This is why part cooling is an important consideration when it comes to the mechanical properties of our plastics. If we cool our plastics too fast and we don't give the polymers time to reorient themselves, then they won't make as many of these bonds between the polymers, leading to basically different mechanical properties for our plastic parts. But if we keep our plastic at that certain temperature range where they can still freely make those bonds, then we'll have stronger parts. So let's extend this logic to 3D printing. A huge issue with part strength is the actual interlayer adhesion between the layers that we lay down. Think about we've already laid down a layer of plastic, and now we're laying another one on top. That other layer has probably cooled past its glass transition temperature already. So the layer added on top isn't going to get to form all these hydrogen bonds or orient itself in a way that can effectively, get the most bonds between the two layers. And remember, there are no chemical bonds in the Z direction. They're only in the X and Y direction. So if you've heard of a process called annealing, this is basically a method to circumvent this issue. Annealing is where you raise the temperature of something, whether it's plastic or metal or whatever, to a certain temperature, and you leave it there for a few hours. And this basically gives the material time to reorient itself, form different crystalline structures. Usually you're doing this to change the mechanical property of the material. In the case of PLA, we're raising the temperature to a point where the PLA doesn't melt into a big heap of plastic, but the molecules can reorient themselves and form these stronger bonds, especially in between the different layers. So what I want to do with part cooling is cool at a point where we're basically cooling as little as possible to still maintain the shape that we are laying down. This will ensure that we're still creating the part that we see in our slicer, and not just a big heap of plastic, but it'll also ensure that the part cools slower, giving us stronger parts. Two things you can do besides changing your part cooling is just to print hotter and slower. You can also print inside of an enclosure while using part cooling, and this will basically make it so that the cooling is less efficient, if that makes sense. You're still cooling that large, like 200 to 60 Celsius very quickly, but getting from like 60 Celsius to 40 Celsius takes a lot longer. So for plastics like ABS, ASA, and nylon, you really do need an enclosure. If you don't use one, you're gonna get very brittle parts. So I know I took a few detours But the point I'm trying to get across is that there's no one-size-fits-all for part cooling. You really shouldn't approach part cooling just setting it at one speed and forgetting about it. I think the material science behind plastics is really cool, and I would love to do a deeper dive into that in future videos. So if you want to see that, stick around the channel. So we talked about why part cooling might be more complicated than you've approached it before, but now let's talk about how we can get the best part cooling. So when I say we're going to talk about how to get the best part cooling, I'm kind of talking about everyday use cases, nothing insane like those CPAP machines that cool your parts. Today I'll be talking about a relatively simple method that can help you get some extreme bridging and overhangs done. If you've seen my video where I tricked out my print head, then you're already familiar with today's part cooling. It's the Hero Me system by MediaMan 3D, also known as Andy. While it's mainly marketed as a part cooling upgrade thanks to these ducts that optimize airflow through them, these days the Hero Me system is really a lot more than just part cooling. The current 7th generation of the Hero Me part cooling system is basically a collection of parts that you can put together in a Lego-like fashion. So if you're planning to stick with the stock parts on your printer, or if you want to get the best parts money can buy, there are going to be parts to put all those together. You can also easily add cool things like these NeoPixels. While I personally love the Hero Me system, there are a few things you should consider before you make the upgrade. Before we get any further, I want to point you towards Andy's Patreon page. On that Patreon page, he's got something like a 50-60 page guide that shows you how to put this all together. He has videos showing you how to orient and support the parts, and you can even get your hands on a magnetic version of the printer. So if you want to swap parts out quickly, you can do that. You can get all that for cheaper than a new roll of PLA. He's put thousands of hours into this project, so go support him if you decide to get it. So this part of the video is really only going to be an overview of the part cooling system and not like a step-by-step guide. I'm also going to touch on some of the pros and cons of the system and talk about something that I think Andy kind of gets wrong about it. But before we jump into the project, let's talk about what you will need to make this upgrade. The first is obvious, and that would be some filament. Since we're printing functional parts that are going to hold your print head together, you're going to want a high temperature plastic that is also very rigid. I recommend using ASA because it has both of these properties, and it's also much lighter than other plastics like PLA and PETG because it has a lower density. You can get by with something like PLA+, but you'll be limited in how you can print. The other thing you cannot overlook is a silicone sock for your hot end. If you don't know already, this is just a small piece of silicone that goes around your hot end and basically prevents air from hitting it, cooling it down. If you install the Hero Me part cooling without this silicone sock, basically the cooling is so efficient that it cools down the heater block so fast that your printer throws a thermal runaway warning. You'll also need some PTFE tubing. You'll only really need a small section, and we'll get into why that is later in the video. The last thing you'll need is a soldering iron. No, you're not going to need to do any soldering for this video, but you'll need to use heat inserts. If you're not already familiar with these, they're these little knurled brass inserts that you can screw screws into, but what you do is you use a soldering iron to press them into the plastic so that you can carefully melt the plastic around them. They make for a really professional look and a very strong way to bind parts together with screws, but you do need something to melt them in place. If you're on the market for a soldering iron, I got this one off Amazon. It cost me about $60 or 3 spools of PLA. I think it's a clone of a more high-end soldering iron, but it hasn't failed me once in the last 3 years. I'll leave a link to that and all the other things I use in this video down in the description. So let's jump right into it. The first step is to download the repository from any of the big 3D printing model repositories on the internet. I typically use Printables.com. It's a .zip file that contains all of the parts that have been designed for the system, all the official parts. There are lots of other parts that aren't part of the official system that other people have created for their specific use cases. So if you can't find a part you need at any point, then search the internet. You'll probably find someone that had a similar situation. After you've got the repository downloaded, you're going to need to extract all the files to another folder. That's because this is a compressed folder. And then we want to select the parts that we want to print out and use for our print head. In my opinion, this is the most difficult part of the whole project. There are so many parts. In fact, they claim that there's like 35 billion combinations. That's one of like the marketing things. The issue is the parts don't really come with a good description. I highly recommend purchasing the like 60-page guide on this from Andy. Even then, it can still be a bit difficult. So for most of the parts we're going to print out, I highly recommend choosing a few of them and printing out a few different kind of versions of it. because more than likely, the first one you choose isn't going to work right off the bat. And it's much nicer to just have them all printed out, so you don't have to stop the project and wait on a print. The first part you need is the gantry adapter. This is basically the part that translates whatever language your printer speaks to the Hiromi language. I printed 2 different versions for my Anycubic Viper, and I also printed this version that lets you mount your tool head to a linear rail. Is that a hint for a future video? Seems like it. So the part that the gantry adapter connects to is called the universal base, and this is a part that everyone is going to need to print. The universal base is the cornerstone of the Hiromi system. This is the part to which all the other parts connect to. On top of our universal base goes the next part, our hot end mount. So the hot end mount is basically what you attach your hot end to, and then you connect it to this, and yeah, Legos. In this video, I'll be using the Mosquito hot end from Slice Engineering. If you want to support the channel, I've got a link in the description to the Slice Engineering website. If you choose to buy anything off of there, then it'll support the channel. The next part isn't one I've used before, but it's called a skirt. Like the hot end mount, it's unique to your hot end. It basically separates the airflow from your hot end fan, cooling down the hot end heatsink, from the actual heater block, so you don't cool that down. It also adds places to mount things like an ADXL or an accelerometer, or things like NeoPixels, which is what I chose to do in this video. If you're planning to run a direct drive setup like I do, then the next thing you'll need is an extruder mount. The extruder mount basically pops on top of your hot end mount. I'll be using the Orbiter V2. The next part is probably the most iconic part of the system, and it is the actual part cooling ducts. Now there are a few different orientations of this. There are some that connect both fans together. There are some for dual fans, different size fans, single fans. There's one for a CPAP hose. Again, print a few out depending on what you're going with. The last big part is the mount for your bed leveling sensor. This is actually 2 separate parts, and it's designed this way so that you can get the optimal configuration for your bed leveling sensor. If you didn't print out multiple versions of anything else, please print out multiple versions of this. You're gonna need it. The goal is to pretty much get your bed leveling sensor as close to the hot end or the rest of the print head so it's compact and looks good. Now, after you've printed out all the main components, there are a bunch of other things you can print out, like cable management towers to help tidy up your wiring. There are endoscope mounts, LED mounts, ADXL mounts. Just explore what's out there. So now that we've got all our parts selected, it's time to start adding heat inserts and test fitting parts together. Starting with the universal base, you'll be wanting to add heat inserts just about everywhere. The first 4 to add depend on your gantry adapter. They either go on the side of the universal base or on the back of it. For instance, the Viper adapter I printed out uses the 4 on the sides, while the linear carriage adapter uses the 4 on the back. Next are the heat inserts for the fan ducts to be mounted. There are 2 inserts on top for your hot end mount and your extruder mount, 4 inserts on the front to mount a hot end cooling fan, and finally there are 2 on the bottom if you're going to use a skirt. After you add heat inserts to the base, it's good to start test fitting parts that you've selected to see what's going to work for you. After you get your extrusion system assembled, this is where you need to add the PTFE tubing. This basically guides filament from your extruder down to your hot end. I forgot to do that until I mounted the print head, so I'm gonna skip ahead a bit, but don't forget that. Also, I always find that the holes that the PTFE tubing is supposed to go into are a bit too narrow from the printing, so I always have to widen them with a drill. I think I used an 1/8 inch drill bit, and that works really well. It still lets the PTFE have a good fit so it doesn't slide around, but you know, it fits. Basically, cut a section that's longer than you need, and then keep putting the extruder on top and cutting off small bits at a time until it fits together perfectly. It's kind of like a haircut. You can keep cutting hair off, but you can't put it back on. After that, I got to work on the part cooling ducts, At first I printed out this set that had a brace between the two because I thought it would make for a more rigid setup. It also had a place for heat inserts here so that you didn't have to use nuts with the screws. Unfortunately, while I was adding those heat inserts, the actual spot that you mount the fan snapped. There's that weak interlayer adhesion I talked about. So I tried to print another set out at a hotter temperature and at a slower speed, thinking that that might make it better, but I tried again and it snapped.
Oh, son of a gun. Not again.
You okay?
Yeah, my freaking thing broke.
Basically, this is what happens when you print ASA on an unenclosed printer, like I did. All the thicker parts seemed strong enough, but it was just these thin bits were too thin, and the ASA couldn't handle it. I ended up printing the dual duct in PETG. It didn't need to be rigid because it doesn't really define the whole structure of everything, but when I went to mount the fans on it, I couldn't even screw them in because I guess the way it was designed, there's no way I'm gonna get a hex driver on the other side of this fan to screw it in. I guess you could use nuts with it and just screw from the other side, but kind of defeats the purpose of it being designed for heat inserts. But luckily, I had taken my own advice and printed out a bunch of versions, and I still had 2 of these single ducts that were separated, and these mounted just fine. Again, that's why you should print multiple versions, so that you don't have to stop your whole upgrade process just to wait on another print. This is especially important if you only have one printer and you're in the middle of modifying that printer and a part breaks or a part doesn't work, and then you have to put the printer back together and then print the part out, and yeah, just don't do that. After getting the ABL sensor mounted, there were only 2 things left to do, and that was the hot end fan and the skirt. My previous setup used this Noctua 4X20 fan. I basically chose this because I wanted my printer to be as quiet as it could be. Unfortunately, as you probably know, Noctua fans run at 12 volts, not 24 volts, which is what my printer ran off of. So I had to add this bulky DC buck converter on top of the print head, which was both ugly and just unnecessary. So I decided to ditch this. Luckily, I had saved my old Viper stock fan, and it turned out that this was just as quiet as the Noctua without having to add this other junk. It was also slimmer and weighed less. I also decided to ditch the fan guard. I didn't think it was that useful. Also, it collected, PLA strings and dust and made some of you quite uncomfortable. After mounting the skirt, I made the last minute decision to add some NeoPixels to the print head. I had some on hand, so I decided to solder them together, put them in the enclosure, and mount it to the print head. After putting everything together, this was the final product. Before mounting it to the printer, I wanted to do a tiny bit of cable management. You could use those cable towers I talked about. Since I have the EBB42 on my print head, the wires don't have to go very far, so I just used 1 or 2 zip ties to tidy things up. Now before mounting the print head, there's one last thing to do, and that is to basically level the fan ducts. The ducts are designed to blow down just under your nozzle, so you want them to be at the same level for one, but also at the right height. So one, you're not blowing on the heater block, or you're not down past the nozzle and, hitting your part or the bed. There's a part that you can print out. You can either print it beforehand or print it on the bed and then just let it cool and move the print head down and do it that way. I chose to do it before I put the print head on. I just thought that was an easier method. You could also just wing it. I mean, maybe it's not that important. After mounting the print head to the printer, I turned it all on and prayed that the magic smoke wouldn't come out today. Yay, no fires. I decided to do a pre-flight check and basically check that all the electronics were still working and that nothing was gonna break. I heated up the hot end a little. I checked the hot end fan, the part cooling fans, and the BL Touch. Then I configured the NeoPixels. In one of my last videos where I replaced all the electronics in my printer, I actually had to define an LED already, so I thought it'd be really simple. But it turns out that the NeoPixels actually need a 4th color defined, which is white, so they're RGBW. Until I figured this out, basically the NeoPixels weren't being addressed correctly, and they would produce either different colors or just the wrong colors outright. But after getting that working and knowing that the NeoPixels weren't broken or nothing was shorted or anything, I loaded up some filament and homed the printer. But before we start printing, there's still a couple things we need to do. The first is basically to recalibrate the printer. The first thing was to redefine the probe offset from the nozzle. This basically tells the printer how far the probe is away from the nozzle. On my print bed, there are 2 holes, so I positioned the probe so that it would fall through one of the holes, and then I wrote down the position it was at, and then I moved the printer so that the nozzle was in the hole, and I wrote down that X and Y position. Subtracting these positions from each other gave me the probe offset. It's important to get this fairly accurate, or else your nozzle isn't going to know the exact height that it's over the printer. So the actual Z height, it could be the exact same, but it could also be, more than likely it will be higher or lower. This could lead to some first layer adhesion issues. It's really not that hard to get pretty accurate, so just take a minute or 2 and do it right the first time. With respect to how high the ABL should be, honestly I never do this the way they recommend, I just kind of eyeball it. As long as the ABL sensor senses the print bed before my nozzle senses the print bed, I'm pretty happy. After getting that sorted out, I did a rough Z offset calibration, just using the normal paper method. I like to use this to get a good ballpark, and then I like to actually observe the first layer being laid down and do a live adjustment of that Z offset to get it just right. I then wash my build plate off with warm soapy water, just to get rid of all the sugars and any debris left on the plate. After getting it back on, I heated the build plate to 60 degrees Celsius and calibrated the first bed mesh. Next, I found my new input shaper parameters, at least just for the x-axis. If you're interested in learning more about input shaper, then check out my last video on it. The final calibration for the printer was just a PID tune. Since we've changed the environment around our hot end and how it cools and heats up, we need to re-PID tune it. Now that the printer was calibrated, I decided to go ahead and retune the filament. I basically did the temperature towers, flow calibration, pressure advance, retraction, all the good stuff. I ended up doing 2 separate profiles, one for 200 Celsius and one for 230 Celsius. The speeds for those profiles were limited by the max volumetric flow, so at 230 Celsius it was about 32 cubic millimeters per second, and then at 200 Celsius it was about 20 cubic millimeters per second. I did this so that I could compare cooling at basically different temperatures and flow rates. The first thing I decided to do was to print out a Benchy. Sort of. It's actually a Voronoi Benchy. I basically printed this out to stress test the cooling and retraction. I also printed out one without part cooling, and amazingly, it actually finished. I did the exact same thing with 2 normal Benchies, one with part cooling and one without part cooling. And really the only thing you can see immediately is that the funnel doesn't look right. But upon closer inspection, you start to see a lot of things, like the gapping on top, you can see the concavity of the hole, you can kind of see the surface finish just doesn't really look that great, but amazingly a lot of the larger features don't look that bad at all without part cooling. So clearly, different features of these prints require different amounts of part cooling. The larger features need less cooling, and the smaller features need more part cooling. So we'd like to be able to tune our printer so that it cools less for when it needs less and cools more when it needs more. Something that you can actually see on the part cooled Benchy is that one side of it looks a lot better than the other side. And this is because of how I had it oriented on the printer. Basically, part cooling tends to be directional. Most printers, like my Prusa Mini, they have part cooling only coming from one side, whereas the Hiromi actually has part cooling coming from two sides. But while it does cover the front and sides a lot better, the back still doesn't get the same amount of cooling as the front and sides. Ideally, we can tune our part cooling so that it blasts bridges and overhangs with like all the air we can get, while it runs cooler for the larger parts. So first, I wanted to start by printing a bunch of parts at just 100% fan speed to kind of show off what the Hiromi is capable of. Earlier I showed the dodecahedron model. It printed this out really well, really no issues with it at all. I also printed out this big lattice structure that basically acts as a bunch of overhang tests at one. And besides a lot of stringing, because I was at 230 Celsius for this, it printed really well. The next thing I wanted to do was check out how the Hiromi did with some extreme bridging. I grabbed this really unique bridge off of Printables that has this cool overhang feature on top, so I imported it into my slicer and I stretched it out, which made the bridges longer and the overhangs even more steep. Check out how the Hiromi handled that. The bridging was pretty amazing at 200 millimeters or longer distances, without much sagging on that first layer that's deposited. But I still wasn't satisfied. I needed to defeat the final boss of part cooling. I considered that to be the pin support model challenge. If you've not seen this, it's basically a model generated that has one long pin support and then you print out an object on top of it. The first one you can print is a cone that is facing upwards, and the other is a sphere, which is the harder model to print. I decided to start with the cone, the easier of the two, and it printed out perfectly first try. Then I generated the sphere G code, uploaded it, and saw how it went. It printed out perfectly, again on the first try, and this is the harder of the models. I mean, these first few layers after the pin support are literally just horizontal 90-degree overhangs. I don't know about you, but I was seriously impressed. So the Hiromi cooling system is clearly a very capable cooling solution, but Andy says that you don't need to run it at 100% speed. He says something like 30 to 40% is all you really need to run it at, and then maybe up to 60 or 70% for overhangs and bridges. So I wanted to test that out and see if that's true. For both the 200 Celsius and the 230 Celsius profile, I printed out these overhang tests from 10% fan speed up to 100% fan speed in increments of 10. So let's start out by listening to how loud the part cooling fans at each fan speed. Now, let's check out the results of the overhang tests. Clearly, at slower fan speeds, there is a difference in how well the overhangs print out. But at the higher speeds, there are diminishing returns. For the 200 Celsius profile, I think that 30 to 40% fan speed worked great for overhangs from 40 degrees and under. But for the more extreme overhangs, from like 50 degrees and above, I would say that they didn't really improve that much past a 50% fan speed. On the other hand, the 230 Celsius profile was a lot more problematic. It showed a clear need for much higher fan speeds on basically all of the overhang levels. So I'd say Andy was right on the money for average printing conditions, so 200 Celsius for PLA, not printing that fast. But when you get up to higher speeds, you definitely need that part cooling cranked up. I also ran a few more of those cool bridges at 70%, 40%, and 20% fan speeds to check out how the bridging would do at different speeds. I'd say that the 70% and 40% looked pretty similar to the 100% fan speed one, but the 20% fan speed is where it starts to fall apart. Now I really think that these bridges could have come out better if I would have slowed the entire print down. Basically, the first layer of bridging turned out really well, but then when you go really fast for those next layers, the plastic that you lay down is hotter, and it either goes between the gaps of the first layer, or it causes the first layer to sag because it kind of heats it up again. So the Hero Me is clearly top of its class for part cooling, but as mentioned, it isn't really for everyone. So maybe when you saw the pen support test, you said, wow, that's really cool, I want to do that. Or maybe you said, why doesn't this idiot just use supports? And I think both of these are honestly fair points of view. The Hero Me part cooling can be a bit overkill depending on how you print. If you mostly do higher temperature plastics and don't really use part cooling, then yeah, you won't need it. If you mostly print PLA but at really slow speeds and low temperatures, then again, you probably don't have a big need for part cooling. But if you want to print at faster speeds, or you want to do some extreme bridges or overhangs, then I think you do need something like the Hero Me part cooling system, or your part cooling just won't be able to keep up with the demand. Now, while I think the Hero Me system is awesome, there are some things that I don't like about it. The first one is just how bulky the print head is. Not only does it look pretty clunky and large and not very agile, I would say it's not very aesthetically pleasing. And if that matters to you, then, you know, sorry. I personally like the approach that the Voron designers took and how they designed their stealth burner. I think that is a beautiful print head. The other issue with the bulk of the print head is that it puts more strain on your printer. Now, while all of the plastic parts don't weigh that much compared to your direct drive extruder, the thing is that it sticks very far out from the gantry. So the more that your print head sticks out from the gantry, the more torque that is going to be applied than if you had all the mass closer to the gantry. And again, that's what the Voron designers did, is they made it tall rather than bulky. And having it tall puts all the force as close to that rotation point as you can, rather than having it further out. Maybe the torque isn't large enough to really matter, but torque typically changes the lifespan of our mechanical parts, makes them louder. In my slow motion clips, I actually found that my print head bounces up and down as it goes. I'm not sure if this would be remedied by kind of reducing that torque, or if I just need a more rigid motion system. But that torque I was referring to was only in the YZ plane. But there's also torque in the XY and XZ plane. The XY torque occurs when the print head accelerates in the X-axis, especially on bed slingers. Basically imagine that your print head is mounted here, but it either hangs too low or hangs too high, like in the case of the Voron one. When it accelerates, if this is where it's mounted and there's some mass up here, this mass is kind of going to get left behind, so there will be a torque applied there. And that's torque in the XZ plane, which I think doesn't really matter as much in the case of the Hero Me system, because it is all pretty well centered around the place where it attaches. The one I think that is more concerning is the torque in the XY plane, and this is again when the print head kind of accelerates on the X-axis. Basically think about like the stuff further out in front kind of getting left behind in that same way. So if this hand is the gantry and this hand is the tip of the print head, or the part most furthest out, then as the gantry accelerates, you're going to get kind of this like back and forth motion there, where the print head will kind of shake left to right. And again, there will be more torque in this plane when the print head is further out from the gantry. You can also counteract this by not having all the mass on one side of the gantry, but having some on the other side as well. The Prusa Mini kind of does this by having its part cooling fan on the opposite side of the hot end. So yeah, that's one thing I don't like, is how bulky it is. The other thing I don't really like is the accessibility of it. Anyone can print the Hiromi system out, but if you don't have a soldering iron, then you're basically not able to have the Hiromi system. I think it could also be designed so that you can use nuts instead if you wanted to. I think the Prusa printers use this approach so that people don't need a soldering iron to put the printers together. But to be fair, that is a lot of work when you consider that I got my soldering iron for the price of 3 spools of PLA. And if you're a hobbyist, it is a good investment, so maybe that's not a big deal. The final issue, again, it's a small issue, but it's something that Andy says about the part cooling system that I think is inaccurate. He claims that he designed the ducts in a way that it produces laminar flow, which is more efficient for part cooling. I would say it's pretty well known, as in you can do a quick Google search and it pops up with a clear answer, that turbulent flow is more efficient in part cooling than laminar flow. In laminar flow, basically there are sheets of fluid, or air, which is considered fluid. There are sheets of molecules that move with the same velocity. And if you have a surface that you want to cool, there's going to be a layer of molecules. There aren't molecules coming in and out of that layer. And the way that heat is transferred is when molecules bounce off of a surface, basically. So if there's a layer there and molecules aren't bouncing off, then basically the cooling isn't as efficient. Maybe by laminar flow he's referring to the flow inside of the ducts, which would make air get to the part you're trying to cool more efficiently. I would say that's fair to say, but I feel like at this small of a scale, it really doesn't matter if your flow is laminar or turbulent. I don't think it'll make that big of a difference. I personally think that saying laminar flow is just kind of a buzz thing to impress people, but maybe I'm wrong. I have heard him mention in an interview that he has someone, I think he set up in New York, that he's kind of partnered with that runs airflow simulations on the parts. I don't know if he's published this anywhere or made a video on it, but I would definitely love to see those results, just because I think they'd be cool. But yeah, just disclaimer, I still really love Andy's work and support him all the way. I just think that laminar flow bit is a bit inaccurate. Yeah, I think that's fair. In the future, I'd love to learn to run my own fluid simulations, but I'm not at a point where I can do that yet. I was thinking about getting some incense so that I could burn and have the smoke kind of, you could visualize the airflow around the printhead, but I didn't get around to it, so I ended up doing the water in a bowl test that everyone seems to do. And at first I thought it was silly, but after I did it, I got some really cool shots. So let's take a look at how the water looks at different fan speeds. These results basically show that, yes, the ducts are pointing the air right where we want them. You can also see at really high speeds that the cooling really is powerful. So, if you're stuck with your stock part cooling, then you probably do need to run your fan at 100% just to get your parts cooled. But the Hiromi, by having 2 large powerful fans and by being designed so well, you can really run those fans at a lower speed, giving you quieter printing and just really quality part cooling. So how should we actually calibrate our part cooling? So I talked about why part cooling might be more complicated and nuanced than you thought. I talked about how to get the best part cooling currently available. And now I want to quickly talk about how to tune your part cooling to get the best results. And by best results, I really mean the best print quality balanced with not overcooling your parts so that you get better mechanical properties out of them. As far as I know, there's not really a standardized way to do this yet. The way I chose to go about it was by doing my normal filament tuning, where I do temperature tower, flow calibration, pressure advance, retraction towers, and then my max volumetric flow rate. I then printed out those overhang tests at all the different fan speeds and increments of 10. I tried doing like a fan cooling tower because I know slicers like Cura have a plugin that lets you automatically generate a tower that does the different fan speeds as you go. I tried doing this with manual G-code inside of Orca Slicer, the slicer I use, but the fan speed would always kick back up to 100 and I couldn't get it working. So I did it this way. You could definitely start at something like 50%, and if you clearly need more cooling, bump it up. If you need less cooling, bump it down. And you're basically trying to find two fan speeds. The fan speed you need for the most extreme overhangs, and the fan speed you need just for the basic printing. So like overhangs 40 degrees and under. Again, the logic behind this is that you can still print things, but you're not overcooling the plastic so that it becomes more brittle, you get worse layer adhesion, all that kind of stuff. But you are still cooling parts that, sections that are either very small and need that extra cooling, or extreme overhangs, or bridging. For my 200 Celsius profile, I found that 50% fan speed was good enough for all my bridging, extreme overhang needs. So I set the rest of the part to be cooled at 20% fan speed. And I printed out a Benchy with those settings. For my 230 Celsius profile, I found that I needed 50% fan speed for my normal part, so the bigger pieces, and then I needed 100% part cooling for overhangs, bridging, and small sections. I again printed out another Benchy, and this is what it looks like. Another thing you probably already know about the different temperatures of printing is that it can change how shiny your part is. I don't know if this is affected by how quickly it cools or if it's purely the temperature that you raise the plastic up to, but again, maybe I'll look into that in the future. So yeah, now we've talked about how to tune. This video took a while to put together. Life has been pretty crazy the last few weeks, so I hope you really enjoyed this or you got something out of it and learned something new. If you want to help me improve these videos, leave some feedback on something you think I did well or things that you think I should do differently. I'd love to hear from you. If you made it this far, thank you so much for your support. It means the world to me. And I will see you in the next video. Bye.